So accuracy is how close you are to the true value. So let's say the true value was 1 gallon, but you came up with 0.9 gallons or 1.1 gallons. Those would be a little less accurate, than the true value. And then precision there are two ways we think about precision. And one way we think about precision is using sig figs, like with the example yesterday, 1 meter. 1 meter, if somebody estimates the length, let's say the width of this table, the width of this table is about 1 meter. Is that fairly accurate? Maybe the width of the table is right on 1 meter, and that's accurate. But was that very precise? No, it wasn't very precise because 1 meter is just an estimate. It looks like anywhere maybe from 3/4 to over 1 meter, something like that. And so the way we think about precision is by the number of sig figs. So we don't know if these measurements are accurate, but we know we can tell something about the precision. And so let me that here. So if I take 3 measurements like this, do we know anything about the accuracy? Well, the accuracy depends on if the true value is 5 grams, then these 3 measurements are pretty accurate. Wouldn't you say? They're right on 5 grams. But there's a big difference in the precision of these. And normally the way I think about precision is I take half the smallest unit, which would be 1 gram here, and half of that would be 0.5 grams. And then what I do is I just say, well, this is going to range from anywhere between 5 plus or minus half of that, 0.5 grams. And so between 4.5 to about 5.5 grams, it would be the range of precision for this particular measurement. And then I do the same thing. Okay, the smallest would be 0.1. The smallest unit here would be 0.1 grams. That's what it reads to. So half of that would be 0.05 grams. And so, we're looking at a precision range of 4.5 to about 5.5 grams. We'll just go 5.4 grams because that would round down. 5.5 should round up to 6. Here we would go from 495 to 505, or we'll go 504 again, so it rounds down. And this would be the most precise because we're narrowing the range down here. And so the smallest increment would be 0.01 grams. And so this would be half of that, 0.005 grams here. And so we're looking at 4.995 to about 5.004 grams. And you can see the range tightens considerably. And so this is one way. So this is a less precise balance. This would be a higher precision balance. Higher precision balances, you're going to pay more for those because they can distinguish or differentiate between small changes, whereas a less precise balance won't be able to distinguish between small changes because the next unit this is going to go up to, so this is 6, or go down to 4. And so it can't read anything between 4 and 5 and 5 and 6. And so that's precision. The other way we think about precision is by agreement between measurements. And so here we have higher precision here. But this doesn't say anything about the accuracy. And then the agreement between measurements would be like this. Let's say I have 4.95, 5.0400, and 5.05. I take 3 measurements, and these are the 3 measurements I get. And what we look at is the spread. What's the smallest, what's the biggest, and how wide is that spread between three measurements of the same thing. So let's say I'm weighing an object. Versus this, let's say I had a 4.54 and then a 5.15 and then a 6.03. If these were the same object, then there's a huge difference in the precision between these sets of data. And so this would be higher precision here, and this would be lower precision. And so when we're observing nature, we take measurements. And so one of the things we look for in measurement is precision and accuracy. What are the other things we consider when we look at measurement? Precision. And then accuracy is usually a function of this. This is what we call higher precision instrument here. Over here, this is a higher precision set of measurements. So what we can do is we can just purchase or build higher precision instruments. But when we have this, this spread in the measurements, this is a result of something called random error. What we could try to do is we could try to improve our technique, in order to minimize random error. And so this is minimized by improving technique or using a higher precision instrument. We can try to minimize random error. This I'll just say technique here. This up arrow is supposed to mean improve. However, random error cannot be completely eliminated. It's kind of weird. You think, if your technique's really good and the balance, it depends. If you use low precision balance, you might always get 5 grams. But, that's because the precision is so poor, the balance. But the random error, when you get higher and higher precision balances, whatever you use, it turns out that this random error can never be eliminated. And you know where that comes from? That actually comes from the theory of chemistry. Do you know what the theory that underlies chemistry is called? Quantum mechanics, right. From quantum mechanics, it's predicted that random error is inherent. That is, it can't be eliminated. It can be minimized, so it's just minimal, but it can never be completely eliminated, which is kind of weird to think about, but that comes from the theory.
So where does random error come from?
Where does random error come from? It's associated with the mathematics of the quantum mechanics. And so quantum mechanics is kind of weird because quantum mechanics is this. Quantum mechanics makes some postulates. And postulates are taken without proof. And so there's certain things in quantum that you have to accept without proof. But the proof is that the predictions and the observations it makes are accurate. And so there are certain things that are, this is probably not a great answer, but it comes from the theory of quantum mechanics. Exactly where, actually, I haven't, that's a great question. I haven't really dealt with it, although I've had lots of them. But this random error, when you minimize it, we just improve technique, so this would be something like this versus this. But there's another type of error that we should be able to completely eliminate. Do you know what that type of error is called? That type of error is called systematic error. And so normally you get poor accuracy by having systematic errors. Let's say your technique is perfect, and what you do is we can eliminate random error. If we take, I should say that it is possible to eliminate random error hypothetically. And do you know how we can minimize random error or eliminate it completely hypothetically? Not quantum mechanics. It's minimized by technique and by
Random selection.
Averaging. Yeah, not random, it's not like a random selection of values. We just take all the values and then average them. And the thinking goes like this. Since it's random, half the measurement should be above the true value, half the measurement should be below the true value, and then they should cancel out. But they're only going to cancel out perfectly if we take how many measurements? Many. And in fact, it would be, we'll just say many measurements. And to completely eliminate random error, let me write that over here since I ran out of room. To completely eliminate, do you know how many measurements we would have to take in theory? So that we get a perfect balance of 50-50, 50 reading too high, 50 reading too low? 50%. I'm sorry? Infinite, yeah. To completely eliminate, we would need an infinite number of measurements. Well, is that possible? No. But there's random error in everything we do. And so, if we're going to have random error, if you just take one measurement, let's say I took one measurement out of these three and it got 6.03, you know, how much confidence can you have in that particular value? So if I just took one measurement and I got 6.03, I'm saying done, I'm good with that. Are you good with that? No, because let's say in the next measurement you got 4.54. And then what's going to happen in the third measurement? No, third measurement, maybe you got 5.15. And so where does that true value lie? Well, we don't know. I mean, so the best thing is to average it. Which one of these three is the most accurate? Who knows? Maybe the next measurement comes out to 7. And the next measurement comes out to 2. You don't know. So what we do is we try to take as many measurements as possible, and hopefully the precision, that is the spread, is a little bit better, you know. Here the spread is a lot closer, so you can kind of get an idea. As long as there's no systematic error, we should be okay. But anyway, the more measurements we take, the better. But taking more measurements takes time. So we typically reach a compromise. You know, of course you want to take hundreds and hundreds, and sometimes you can do that because I've done some experiments where I can take a reading every microsecond, and so you can get millions of data points and then just average those. But other experiments take all day long. You know, let's say to get these samples, you had to do 2 days worth of lab work. Well, how many experiments do you want to do? You only have a finite amount of time. And so there's some statistics that go with this, you know. And the statistics say, what's the best, you know, the trade-off, the best trade-off? What we want to do is we don't want to just take one measurement because the risk is very high that the uncertainty is pretty good. And so 2 measurements is better. But 3 measurements is better than that. 4 measurements is better. But 1,000 measurements, you know, is it much, much better? Let's say I took 999 measurements, but I said, oh, okay, I'm going to take 1,000 measurements because it should be much, much better. It's going to take me 2 more days to get 1,000. So to go from 999 measurements to 1,000 measurements, is that good cost versus benefit? Do you think I'm going to get a much better answer? No. No, so the difference between 999 and 1,000 measurements isn't so significant. But the difference between 2 measurements and 3 measurements is a big jump up in confidence. And this comes from statistics. From statistics, it turns out a 4th measurement, yes, would be better, but not as good. It's non-linear. So 2 measurements is a huge jump. 3 measurements is a pretty significant jump. 4th measurement is a small jump in improved confidence in the average. And so normally the trade-off comes with 3. You know, 4 is better, sure, but if it takes a lot of time, do at least 3. And so typically in a lot of science experiments, we collect 3 samples. That way we get a good statistical average. And that's for minimizing random error. Now, the problem is let's say these are weighed on a balance. Is the balance reading accurately? And so this is what I was saying about yesterday. No, these things have to be calibrated. You go to the supermarket and you'll see that somebody checked the calibration on their balances because you're paying for, let's say, fruit or whatever else. You want to make sure the balances are reading accurately. And so that's a function of systematic error. If the balances are, let's say they're reading systematically too high, let's say the actual mass is 4.5 grams, but you're reading closer to 5 grams, then that's a systematic error. The balance needs to be recalibrated. And so calibration is important for eliminating systematic error. Systematic error happens when we have a bad technique or poor calibration. A bad technique would be you're misreading. You're misreading the meniscus. Some people read the meniscus from the top. Some people have parallax where they read it too low or too high, and they get an incorrect reading. So systematic error is due to poor technique or calibration or calibration. So the balances that we use are calibrated before every semester. So we start off the semester with calibrated balances. Sometimes these instruments can drift and give incorrect reading, and those would be systematically too high or systematically too low. Sometimes systematic errors are hard to avoid, so we correct those. So for example, when you read the mercury barometer, the mercury expands or contracts with temperature. And so if you're reading a mercury barometer, you're supposed to correct that. And so we have a systematic correction for that. And so depending on the temperature, the barometers are calibrated at 0 degrees C. So at 25 degrees C, they expand, and the calibration, the mercury is about 1.2 millimeters too high. The reading is. All right. So you should know precision, accuracy, random error, and systematic error. All right. That's for observation. Observations are measurements. And scientists like to take quantitative observations versus qualitative observations. What's the difference between quantitative and qualitative observations? I'm sorry? What is the difference between qualitative and quantitative observations? Uh-huh.
Qualitative is the quality of what's going to be doing, and the quantitative is like from quantity, how many times we do this in order to reach the
It's a little bit not. I mean, in chemistry we don't define it that way. We have a different definition for it. Actually, quite a significant different definition for qualitative versus quantitative. Excuse me. They both deal with numbers. Ashley? Yeah, they both deal with numbers. Well, go ahead. What were you about to say?
Like how things seem to change versus like the values that we measure. Like because the quantitative has to do with like mass and things like that, and like pressure. But maybe qualitative has to do like if it changed colors.
Okay. No, that's not the way we quite do it. In terms of measurement, a qualitative versus quantitative. A qualitative would be an estimate. A quantitative would be a more precise, more accurate measurement. Estimate versus more precise, accurate measurement. So a qualitative measurement would be like there were 1,000 people at the concert. A quantitative measurement would be, well, we counted 998 people, not 1,000, you know. So 1,000 would be an estimate, you know, 998 would be quantitative. Does that make sense? In analysis, we have a slightly different definition too. Have you done qualitative analysis? I assume you've all done qualitative analysis. We have two types of analysis. In qualitative analysis, what do you analyze the solution for? For the presence of particular ions. You know, you looked for things like silver ion. Do you guys remember doing this experiment pretty much? And that's qualitative. Is it there or is it not there? Can we detect it or can we not? If it's not there, maybe it was there, but in too low of a concentration to detect. That's qualitative. In quantitative analysis, we not only want to know what's there, but we want to know how much. You know, how much is there? Is it 5 parts per billion, 10 parts per billion, 10%? We want to know as precisely and as accurately as we can what's in it and how much. And so this is different. And what other topics in measurement, vocabulary that we need to know for measurement? You know, certain things that we measure could be extensive or intensive properties. And there's a difference in how we measure those types of things, extensive versus intensive properties. We usually measure properties. Properties could be like color, weight, volume. You know. But when we're measuring these types of things, extensive versus intensive, and the thing that people use often, extensive versus intensive, you probably heard this many times, is what weighs more? You know, what weighs more, a pound of feathers or a pound of gold? They both weigh the same, right? Pound of feathers and pound of gold. Because that's an extensive property. Extensive would be depending on the amount, versus the intensive property would be different. What would be the difference between a pound of feather and a pound of gold? Well, one thing would be one of its intensive properties. Its intensive properties would be what? Density. Density is an intensive property. So an extensive property depends on the amount. Intensive property is independent of amount. And so it doesn't matter how many feathers or how much gold you have. The densities are dramatically different between gold and feathers. Right? And so this is independent of amount. And so these things we keep in mind when we're taking measurements and when we're observing nature, because those are the things. Care about. All right, so we take as quantitative measurements as possible, keeping all those things in mind. Are we what types of things are we measuring, etc. And then the process would be, okay, from observations we go to what? It's hard to go straight to hypothesis. We go to patterns and trends. In other words, usually we collect tons of data. The amount of data with the temperature is minimal. But normally, if you're collecting 1,000 data points, that's a lot of data to look at. Let's say you put 1,000 papers on your floor and stare at that. That wouldn't be very effective. So what we do is we do a process called data analysis or data reduction. You know, we're reducing all that into a pattern. What's easier to remember, 1,000 individual data points or some kind of pattern or some kind of trend? You know? Like if you're given a data table of Celsius versus Fahrenheit and you have 1,000 different measurements there, is it easy to see the pattern or trend there? No, that's not easy. And oftentimes we don't even have to go to a hypothesis. A hypothesis is at a deeper level. Can somebody define what a hypothesis is for me? A hypothesis is a tentative fundamental description of the underlying observation or underlying pattern or underlying law. You know, it's what's happening at a more fundamental level. And so it's a fundamental description of what's going on. And so normally what we do is data reduction and analysis. Data reduction is we're reducing all that data into a pattern, into a trend. Patterns and trends are much easier to analyze than individual data points. And so we do data reduction and then data analysis. And if that pattern or trend holds still and we can define it mathematically, then we call it what? A mathematical pattern is called a law. Most of these laws are empirical. Empirical means what again?
Observation.
From observation. Right. And so most of these are empirical laws. And then from the law we go to, now if we want to go deeper, a lot of times we don't. Like PV equals nRT, have you thought more deeply? I mean, where does it come from? Why is it PV equals nRT? Yeah, it just comes from the patterns, the observed patterns. Well, you know, what's the proof for that? Well, there's not really a proof for that. Actually, there is. What people have done is PV equals nRT comes from observations, but what people have done is they've gone from quantum mechanics and used quantum theory to derive the ideal gas law. So kinetic molecular theory is all part of quantum. And so from quantum to kinetic molecular theory to the ideal gas law. So it has been derived both from observation and from theory. And so that's another success of the theory. But a hypothesis, we don't necessarily have to go, you know, it would be great to, and this is what we call a fundamental description. What scientists do is they just describe what they observe. You know, if this is some pattern you observe, that's it. It's a pattern. And so scientists are good at describing nature, but science doesn't answer some questions, though, too. Science doesn't answer certain, like, why questions, you know. I mean, why is there, like... But that's not, you know, that's the part of that, you know, science... This is the good thing about science is science sticks to the scientific method. And science sticks to the scientific method, then you can have good trust in science. You know, there's a lot of mistrust in science now. A lot of people don't trust science because people kind of overextend, you know, and make, you know, certain statements or something that aren't, you know, or a little bit beyond. You know, we just observe, like this guy who's, you know, at Harvard. Actually, you know, you read his paper, a lot of people are, well, you hear his talk, and he's talking about, you know, there could be intelligent life forms out there because to make certain structures or to make certain composition alloys would have to be synthesized because they shouldn't occur naturally. According to what's been observed. And so, you know, but you read the paper, he doesn't make any mention of those, he just talks about, in other words, he sticks to the science, so, you know, he's unfairly criticized, I think. But most scientists, we stick to this, stick to describing nature. All scientists try to do is describe what's observed. And that's pretty much it. And so that means there are certain things outside the realm of science. Of course, you want to know other things, but, you know. And so this is the beauty of the scientific method, and this is why it's worked for so many decades, going on centuries now. And so this has brought about excellent development. And so the fundamental description here is tentative. But eventually this should evolve into a theory. So what has to happen is the hypothesis has to be tested and challenged. And then we have theory, which is also a fundamental description. The experiment would be tested. We test everything with experiments. And experiments are for observations, experiments are for everything, basically. So experiments are going to be included. Here, even when we get the patterns and trends, we don't rely on one pattern, one set of experiments. We usually do multiple experiments and have to reproduce them. So experiments are continually in this as well. And so you could say experiments. And so theory is going to be a fundamental description, but it's going to have widespread acceptance, and two, it's got to predict, right? And so these are the steps, step 1, 2, actually 3, 4, this is typical. It could go on, 5, 6, whatever, or fewer. Sometimes certain things happen serendipitously, through serendipitous observation. Like penicillin. That doesn't quite fit this pattern, but this is kind of the pattern that most people stick to. So the purpose of the scientific method, what would you say the purpose of the scientific method is? Uh-huh.
To make sure that people can replicate it?
Yeah, to make sure that people can replicate it. And it's also not just replication is part of this testing. Even these patterns are tested. These patterns are tested, like in the social sciences, when they look for patterns, versus in the sciences we look for patterns. And there's a statistical quantity. Usually when we look for patterns, we graph it. In the social sciences, I was listening to some social scientists, and they said they get an R squared, which is a correlation factor. Like R squared of 1 means it's perfect. Your data correlates perfectly with whatever your hypothesis is or your pattern is. In the scientists, we need R squareds in the multiple nines, 0.999 or 0.998 or something like that. In the high nines, we want an R squared value because that means that the pattern fits your mathematical equation. Usually we try to fit these patterns mathematically, empirically, with some equation. And so that means it's an excellent fit. But in the social scientists, they said, I heard R squared of 0.68 is good. A 0.68 in science, in the hard sciences, is not good at all. It's a very poor correlation. And so it depends on what the expectation is. So in the social sciences, the expectations are a little bit different. In the sciences, a little bit different. And so by conforming to this, then we could have good confidence, in the theory, in a particular theory that's been developed and tested like this. And so the purpose of that is to have some way to challenge these types of things. And then we talked about some properties of matter, classification of matter, SI units. What we're going to do today is we're going to zip through where was it? Density and percent composition, their use in problem solving. Actually, we're going to focus the rest of the chapter on problem solving. And density is one of these conversion factors that we use. Density is an intensive property. It's mass to volume ratio. So density for pure substances doesn't change, like gold. It's easy to tell the difference between gold and fool's gold based on the density. Also, the crystal shapes and other things can clue you in to the difference between fool's gold and real gold. But osmium is interesting because do you know what the density ranges from? Like wood. You know, is wood more dense than water or less dense? Most wood floats on water, so it would be less dense. I don't know if there's any wood that sinks in water, unless it's like waterlogged or something, then it might sink. But what is the density of water? Everybody should know the density of water approximately. It's easy to remember. It's an easy number to remember because it's 1. It's 1 gram per milliliter. That's the density of water, 1. But how precise can you be?
Isn't there like a, I forgot what it was, wasn't there like one of the experiments like something that was like 0.99?
Right. So you remember the density table of water. Okay, let's take a look at that quickly because I'll talk about data reduction here. So normally we collect a lot of data. Let's see if we have a data table here. So here's our data table, 3 pages of data. That's a lot of data on the density of water. This is the density of water at different temperatures. And then what we want to do is we want to do, what's the next step? Are you going to come up with a hypothesis now? Would it be easy to come up with a hypothesis now? No. So what we do is we look for the patterns and trends. Is there a pattern to all these numbers? Well, let's take a look. When okay. Gosh, I wanted to. Let's just pick one of these. All right, sorry, it's hard to read, but do you see a pattern to those numbers? Yeah, it looks like they're going up and going down. All right, then what we do is we try to look for, normally in science we graph these things via a graph or chart. And we can see the pattern here. Let's see. So if we take all that data and graph it, you can find a different one. This is a good one here, maybe. Okay, no. It's not going to give it to me. We'll do it this one here. We see this. If we zoom in at the first part here, they're doing the density in different units. Do you see what the units here are? They're doing SI units. SI unit for density is not grams per milliliter. You know what the SI unit for density is? The SI unit for mass is kilograms. The SI unit for length is meters. And volume is what we call derived unit. And so it's just meters times meters times meters, so it's meters cubed. So they have the density in kilograms per meter cubed. So you see where it says 1,000, that would be 1.000 grams per milliliter. Now the density of water is not 1 gram per milliliter because you can see the density of water changes with temperature. Well, the first thing is, does it change that much with temperature? Not really. I mean, we go from 1.00 all the way down to about 0.96 as we get closer to the boiling point of water here. So well, maybe it did change. It changed about 4%. Right? The density did change. But there's a weird thing that happens right, if we zoom in right at the beginning. Do you know what happens with the density? Where water is the most dense is not at 0 degrees C. Do you know where water is the most dense?
It's at 4 degrees.
Yeah, 4 degrees Celsius. That's where it's most dense. Well, and so we can zoom in on that area and see where it is. There used to be so many good graphs here. Here you can see it. And so the density of water peaks here, 1 gram per milliliter, at about 4 degrees Celsius. Okay. And then if you cool it down closer to 0, the density drops and you increase it. And so what we do is we have the pattern there, and then what we try to do is we try to model it. The way we try to model it is we try to get a mathematical equation that fits that. You could just use a chart. A lot of people use a chart. They go, okay, what's the temperature? Oh, this is the temperature. And then they go up here, and then they go over here, and they figure out what the density is. That's called graphical analysis. So we could use a chart for graphical analysis. But a chart takes up a lot of space and it takes time to generate. What would be better is to define this curve as a mathematical equation. As if it's a mathematical equation, we plug into x, we solve for y. Y is the density here. And so that is called fitting the data. And so what is the mathematical equation for the density of water? And so we can, you guys use the data table itself, and you guys use the equation, this is also in our book, in one of the homework problems. Oh gosh, come on. I should probably look it up on Wikipedia. Here it is. What does empirical mean? From observation. So based on that data table, this is the equation that they came up with for the density of water. And so the density of water is equal to 999.99399 plus 0.042 T minus 0.00709 T squared plus whatever. It's a polynomial function. And so what you do is you plug in the temperature here and solve for the density. So this would be the empirical equation that defines that. Okay, this would be the law of density. If this one works, if this equation fits it, it depends on the R squared. If the R squared value is 0.68, it's garbage. It's not going to give you an accurate reading. But if the R squared is in the high 9s, then you can be pretty confident that this equation is going to give you the correct density. So we just plug in the temperature, get the density. Now, that's the law. This would be the law of density of water as a function of temperature. Okay, then what would we do? We'd go, that's not enough. Now, the next step would be to do what? Next step would be, why does water contract to 4 degrees C and then expand to 100 degrees C, the volume? And so why does it get smaller and then bigger? Do you have a hypothesis? Tell me your hypothesis. Tell me why water contracts till 4 degrees and then expands after 4 degrees. What's special about 4 degrees? Who made that number? No, science doesn't say who made that number or what's special about it. Science just says, well, that's what happens. It's a description of nature. Nature does that. And so what we want is, we don't want to say why. Why not 5 degrees? Why not 6? We don't say that. We just say it contracts to 4 degrees and then expands. And then what we want is, we want a fundamental description. What about the water molecules is doing that? Science is a fundamental description of the underlying phenomena. So if the water is contracting and then expanding, then we should be able to describe it, using structure, composition, and properties, correct? And so the next step would be, sure, I got this equation. It's a higher order polynomial. I think it's 3rd order or 4th order polynomial. And then no big deal, because you can punch these in your calculator. Solving for T would be hard, but solving for density would be easy. Just plug in the T's. And then we, once we get that fundamental description, then if it has widespread acceptance, then then it'd be a theory. So some people hypothesize there's something called polywater, or some people might hypothesize that there are little, little things entities, bodies, and they're pulling them together and then releasing them or something. I don't know. You could have lots of different hypotheses. You can make any hypotheses you want, but the scientific method will test those hypotheses, and you want reproducibility. You want other people to be able to reproduce it. And so that's the beauty of the scientific method. There. And that's why it's been so successful, and that's why it's kind of frightening if we deviate from the scientific method, because then people can't trust science. But you should be able to trust science because it does something very simple. It just tries to describe nature. That's it. All right. So anyway, osmium is a really interesting one because densities vary from something like wood. Wood is like half as dense as water. So water has a density of around 1, but it changes, of course. It depends on the temperature, but we can just say it's around 1. And you might be off by 4%, depending on what temperature you are, but 4% is not huge. It's not like 50% you're off by. And so wood is like pine wood is a density of about 0.4, and the hardwoods have a little higher density, than that, about half as dense. Gases are about 1,000 times less dense. If you try to submerge a helium balloon versus a piece of wood, it's a lot easier to submerge a piece of wood than a helium balloon. Right? And so gases have a density of about 1 gram per liter, roughly. Water is about 1 gram. Most solids are around 2, 3. Aluminum is about 2.7. Iron's about 8. But what's some of the most dense stuff that you know? Like gold. Do you know what the density of gold is roughly? Not 200. A lot less than 200. Less than 22. It's an easier number to remember. 20, right? The density of gold is about 20 grams. This is about 22. Osmium and iridium are 2 of the most dense elements. I forgot which one. They're very close. Osmium and iridium are the 2 most dense elements on the periodic table. They're denser than gold, but not that much denser. Gold is 20. These are about 21, 22. And so osmium and iridium are pretty rare. You don't really see those that much. This is a bizarre question here. What is the mass of a cube of osmium that is 1.25 inches per side? And this answer here is wrong. But we're going to skip that particular question here, so ignore that. I don't know what they're talking about here. I'll have another question mark. This is a scale here. This is a spring. Weigh it. I don't know what that is. But weighing it is pretty easy, but determining its volume is, this is buoyancy. Measuring the volume, we usually measure volume by displacement of water, and we need a grad cylinder, or we need something that has graduations here so we can measure the volume. And so we, although the strings are going to lead to air and other things, but this is completely submerged. If you completely submerge it, then water will be displaced. You've done this before. Have you done this before in measurement? Yeah. That's for irregular objects. Okay, we talked about systematic errors, random errors, precision and accuracy already. Which one's more precise? The one on the right. Which one is more accurate? Usually you would think the one that's more precise is also more accurate, but we don't know because of what? Yeah, right. We don't know. I mean, is it broken? Is it working properly? Has it been what? Has it been calibrated? That's the most important thing. In accuracy, if you want accurate measurements, you have to make sure the measuring instrument is properly calibrated. That is, the reading that you have here is close to true value. And so there's quite a big difference in the precision of these two balances. and cost. In Chem 4, we use these. Actually, we have one more digit of precision. So we call these centigram balances. This is a tenth of a gram. The next one would be centa, a hundredth of a gram. The next space would be a milligram. And so when we look at this one, this is a tenth of a gram, centigram, milligram, and tenth of a milligram. And so a tenth of a milligram precision, because this would be like 7 milligrams, this would be 8/10 of a milligram, are expensive. These are $5,000 balances. In Chem 1A, we're going to use these $5,000 balances. Actually, 5,000 pre-inflation. I don't know what they are now. Sig figs, I'll let you review that on your own. How to use the calculator, I'll let you review that. End of chapter, not quite. What we're going to do is we're going to take a look at some example problems. So I'm not going to call this end of chapter. I'll call this example problems. How late do we go to today? 11:15? All right, so we're going to use conversion factor technique for calculations or dimensional analysis. And let's take a look at some problems from the book, which I had written here. Get the I'm going to take a look at 67 and 75. Our book has a section of advanced problems. And we're going to just start off with an advanced problem here. According to the rules on significant figures, the product of the measured quantities, okay, so we have 99.9 meters and 1.008 meters. How many sig figs here? Here? 4. Should be expressed to 3 significant figures. Because if we do a product, then we take the fewest sig figs and we express the answer to the fewest sig figs. So 101 square meters. Yet, in this case, it would be more appropriate to express the answer to 4 significant figures, 100.7 square meters. Why?
Maybe because the one is when you say sig figs measures something that point.
Yeah, pretty much like that. You know, when we think about the uncertainty here, the uncertainty is going to be like, well, let's just look at the last digit, 0.1. So we've measured it to the nearest 0.1 meters. So that's 0.1 out of about 100. And over here, what did we measure? We measured it way more. And so it looks like our uncertainty is at the 0.1 out of 100 parts. And over here, our uncertainty would be 1 out of 100 versus 0.1. So 0.1 out of 100 would be 1 out of 1,000. So if we made this like 999, then we're about 1 unit per 1,000. Over here, we're 1 unit per 100. Over here, expressing it like this would be like more 1 unit out of 1,000, because this would be also about 1 unit out of 1,000. Does that make sense? So in terms of proportionality, this would be more than this. But that's the problem with sig figs. The rules for sig figs are easy to use. However, that's not the way we do it in science. What we do in science is we do something called propagation of errors. Propagation of errors usually requires some calculus to do this. And so when we do error analysis and we determine what is our confidence in this in terms of sig figs, then we figure that out using propagation of errors. Propagation of errors are probably, you can use algebra to do it, but we haven't done it in chemistry. And then in chemistry, we've always taken the easy way out. The easy way out would be sig figs. The hard way would be to do a proper analysis. So sig figs isn't perfect. It works well, you know, but you have to keep in mind sometimes it's not correct. And this is an example of where sig figs, the rules for sig figs fails. Rules are different than laws. You know, the difference, the way I think about a rule versus a law, you know, a law has to be reproducible, like the ideal gas law. You have to have confidence that you're going to get the correct answer. And so laws are going to have a certain degree of reproducibility and fewer exceptions. You know, the number of exceptions we expect for laws is minimal. But for rules, rules can have lots of exceptions. You know, you can break the rules. It's not a problem. Like solubility rules. Have you heard of the solubility rules? What other rules have you learned in chemistry? Nomenclature rules? You know, there's always exceptions to these types of things. What was the other problem I was going to do? Right. So that's the rundown on that. The other problem I wanted to look at, actually more if we have time, 75. Okay. In the United States, the volume of irrigation water is usually expressed in acre feet. 1 acre foot is the volume of water sufficient to cover 1 acre of land to a depth of 1 foot. And then they give us some conversion factors here. 640 acres is 1 square mile. 1 mile is 5,280 feet exactly. The principal lake in the California Water Project is Lake Oroville, whose water storage capacity is listed as 3.54 times 10 to the 6 acre feet. Express the volume of the Lake Oroville in cubic feet, cubic meters, and US gallons. Okay, so let's go ahead and do this problem as an example here. So I'm just going to copy this over to the PowerPoint. And so what we do is a dimensional analysis. You know, we don't even have to know, you know, where does the acre come from, you know, et cetera, et cetera. They just tell us here. And so we have this. This is our given. Normally we start off the given with an extensive. We don't start off with intensive. Both of these are intensive characteristics here, like the conversion between acres and miles squared and the conversion from miles to feet. These are intensive. So we look for something extensive like this. And that's going to be our starting point. So we start there, 3.54 times 10 to the 6 acre feet. Now this is a composite unit. Lots of times we have composite units. Examples of composite units would be something like this: grams, what was it? Grams, heat capacity. Grams, actually I should say joules per gram degree C. This is an example of a composite unit. Joules on the top, grams degree C on the bottom. This is something for specific heat. And so oftentimes we have these and we just cancel, you know, individual units. So the equation for specific heat is Q is equal to MC delta T. And so C is joules per gram degree C. We got to cancel out grams, so we cancel it out by multiplying by mass. We got to cancel out degree C. We cancel it out by multiplying by temperature. So if we multiply by the mass, that cancels out the grams. If we multiply by the temperature, we cancel out the degree C, and we're left with joules. Well, Q is joules. And so we do the same thing here. We have a composite unit, acre and feet, so we got to cancel out. Well, I want to cancel out acre. And so when I do dimensional analysis, I have no idea where I'm going. I just need to cancel out acre, or 3.54 times 10 to the 6 acre. And so hopefully I can cancel out acre. Well, I can, because there's something here that tells me where to go. I can go from acres, 640 acres, to 1 square mile. And so that gets rid of the acres. But I don't want miles there. I want feet, because I want cubic feet. So I'm going to leave feet in there. But the miles squared, I need to get rid of that. But I have no knowledge of anything with miles squared. So what I'm going to do is I'm going to put miles here and then square the whole thing. And then I have something here that takes linear miles and goes to feet. And so I'm going to just go 5,280 feet to 1 mile and square everything. So this would be 5,280 squared, feet squared, 1 squared, miles squared. And that's going to get rid of miles squared. And now I have feet squared, but I want feet squared because a foot squared times a foot gives us foot cubed. And so this is dimensional analysis here. I get foot cubed, and then I just punch in the numbers. Bring my calculator. So I brought my calculator, and see if you get the same number I get. And so I have 3.54 times 10 to the 6 divided by 640 times 5280 squared. And I get 1.54. How many sig figs am I allowed? Well, this has how many sig figs? This is 3 sig figs. How many is this? This is actually infinite. This is by definition. Although it doesn't say it there, it's by definition. And this is, by definition also, infinite sig figs. And so we're allowed 3. So if we're allowed 3, I'm going to write 4 here, and then show the drop digit, and then times 10 to the 11. And then I'm going to do one more step here where I round. So this is going to round to 1.54 times 10 to the 11 cubic feet, or square feet, sorry. No, cubic feet. Actually, we want cubic feet. And so that works out. So about 154 billion cubic feet of water. So if we want cubic meters, we kind of do the same sort of thing here with cubic meters. I just start the problem over again. Actually, let's do, maybe we'll do, I don't know, maybe we'll do, oh well, we'll just do these really quick. So I start the problem over again, starting at 3.54 times 10 to the 6 acre feet. And the first step is to get rid of the acres. So 640 acres per square mile. And the second step would be to get rid of the square miles. So 5280 feet per mile, and square the whole thing. The next step would be to get rid of cubic feet. And so what I'm going to do is I'm going to go linear feet. 1 foot is equivalent to 12 inches, and cube that whole thing. And so the acres cancel, the mile squared cancels, and all the feet cancel. And now I have cubic inches. But I don't want cubic inches, I want cubic meters. So I can go from inches to centimeters. 1 inch is exactly 2.54 centimeters. And now I'm going to cube this, and that gets rid of cubic inches. And now I have cubic centimeters, I want cubic meters. And so there are 100 centimeters in a meter, and then cube this whole thing. And so the cubic centimeters cancel, and that gives me cubic meters. And so once I have cubic meters, then I'll just punch in the numbers, and let's see if you get the same answer I get. Those 3.54 times 10 to the 6 divided by 640 times 5280 squared times 12 cubed times 2.54 cubed divided by 100 cubed. And I get 4.36. Looks like, again, all these are exact conversion factors. So I'm going to get 4.36, and I'm going to carry 1 extra, the dot digit, which would be 6. 4.366 times 10 to the 369 times 10 to the 9 cubic meters. Is that what you get? So this should round to 4.37 times 10 to the 9 cubic meters of water. Yeah, let me check it after. Well, let me check it later, afterwards. Is that okay for this? You could try the gallons one. With the gallons, we're going to need this conversion factor. 3.785 liters is equivalent to 1 gallon. This is 4 sig figs. And we're going to need one more conversion factor, and that is 1 cubic centimeter is defined as 1 milliliter. And so if we use these two additional conversion factors, then we can convert it to gallons. All right, there's actually there's more problems I want to look at. There's another problem here in the book I'd like to look at, which would be conversion factors. Some of the conversion factors you have to be very careful of what you're talking about. In other words, you have to label things. And so I'd like to try, at least start this here, number 69 here, just to show you what to beware of in this particular problem. You just insert. We have to be careful of what we're talking about, and so I didn't really talk much about percentages, but I want to talk about percentages right now. When we express composition, there are different ways we can express composition. One of the common ways of expressing composition is by using a percent. And so if we're looking at percent A, then typically this is by mass. And what that means is we're going to have grams or pounds of A over 100 grams total times 100%. And so let's say we had 50 grams of A out of 100 grams total, that would be 50%. You know. If it's 100 grams of A over 100 grams total, then it'd be 100% A. But sometimes the composition is very low. Let's say we only had 0.001 gram of A out of 100 grams total. That's very low. And so you're going to get a very small percentage. When we get very small percentages, we like to use other types of units. So in other words, we like to use things like part per million. In fact, let's just start with part per million A. If we do part per million, it's the same thing. We look at grams per A per, actually, this is wrong, sorry. This is not 100 grams total. This is just grams total. This is, sorry about that. This is grams of A over grams total times a million ppm. So let me do that in different ways. So an example of this would be, let's say I had 36 grams of A over 100 grams total. You know, then we times this by 100% and we'd get 36%. But let's say I had a very small number. Let's say I had 0.000036 grams of A over 100 grams total. Then the percentage is going to come out quite small. So times 100%, and that's going to give me 0.000036%. And so when we use this, that's a lot of zeros to insert in there. And so it'd be easier using ppm. And so if we use ppm, let's say I had 0.000036 grams of A over 100 grams total, and then I convert this into ppm, I'd multiply this by a million ppm rather than 100 per ppt, parts per 100, or pph. And so if I do that, this would be 10 squared, this is 10 to the 6th, it would be 10 to the 4th, and this comes out to 0.36 ppm A. So ppm, oops, we're out of time here, so I'm going to stop here and do that. But ppm is used for small amounts. All right, did anybody miss roll?
That probably did. Lopez just.
Okay.